Modern physics faces a deep, persistent contradiction. The continuous geometry of gravity refuses to integrate with the discrete mechanics of quantum states. As we push towards extreme limits, the smooth foundation shatters. At macroscopic scales, Einstein's field equations provide a highly precise description of how mass curves space and time. But inside regions of extreme density, like the interior of a black hole, these equations reach a point of mathematical breakdown. They produce infinite values and lose their predictivity. The theoretical failure centers on diffeomorphism invariance. This is the mathematical requirement that the space-time manifold remains smooth and continuous under coordinate transformation. At high energy limits, this assumption becomes physically untenable. This loss of predictivity suggests the four-dimensional space-time manifold is an effective, coarse-grained description emerging from a more primitive, high-energy substrate. Previous attempts at quantum gravity have tried to bridge this gap. Loop quantum gravity models discrete loops to quantize the metric tensor. Other approaches utilize causal sets to map progression. However, the solution may require quantizing structures deeper than the metric. Resolving the conflict between relativity and quantum mechanics requires mapping the mechanics of that underlying high-energy substrate. The variable slice density model, or VSD, provides this map by synthesizing relativistic block universe ontology with the many worlds interpretation of quantum mechanics. The many worlds interpretation proposes that all possible alternate histories are physically real, representing branching universes. Relativity relies on an eternalist philosophy. In a 4D block universe, past, present, and future coexist as fixed coordinates within a static manifold. While consistent with relativity, a traditional block universe is too classical to account for the branching behavior observed in quantum systems. VSD integrates the many worlds mechanism of unitary evolution. Instead of the wave function collapsing, it physically dissociates into independent, non-interacting components through decoherence. At macroscopic scales, this leads to absolute decoherence. Absolute decoherence occurs when interference between distinct classical 3D geometries is completely suppressed because they lack a common mathematical background. These decohered branches exist as static, parallel pathways physically embedded within the 4D geometry of the block. Reality consists of a timeless, highly structured 4D manifold populated by a varying density of these parallel 3D geometries. The fundamental units of this 4D block are discrete configuration vertices mapped within a relativistic Hilbert space. A Hilbert space is a mathematical structure used in quantum mechanics to represent the state of a system through a set of vectors. To preserve the total count of states across the manifold, the model employs a normalization condition for the slice density, denoted by the Greek letter rho. This visualization represents the 4D manifold as a series of stacked 3D planes. The slice density is not uniform. Mass causes these configuration slices to cluster or bunch together. This bunchiness. Specifically, the VSD model proposes that the lapse function, which determines the rate of proper time flow, is inversely proportional to the slice density. As an observer's world line passes through a high-density region, it traverses a larger experiential budget of configurations. Because the lapse function is small in these high-density regions, proper time passes more slowly relative to distant coordinate time. This structural traversal reproduces gravitational time dilation without invoking force fields or graviton exchanges. The force of gravity emerges as an observer's perception of navigating a pitched, highly dense informational geometry. To match the predictivity of general relativity, the VSD model must explain how stress energy sources this bunching according to specific mathematical rules. The model builds on the work of Ted Jacobson and Eric Verlinde, framing gravity as a thermodynamic equation of state rather than a fundamental interaction. In this framework, gravitational action is defined by the quantum relative entropy between the discrete substrate and the effective metric. Quantum relative entropy is a thermodynamic measure of the informational distinguishability between two quantum states. Applying the principle of stationary action to this informational Lagrangian derives the field equations. The principle of stationary action states that the path a physical system takes is the one where the action integral is minimized or maximized. This derivation reconstructs the rules governing the Einstein tensor, the mathematical object representing the curvature of spacetime. Rather than merely replicating known metrics, this provides a foundational framework for predicting geometric behaviors within the substrate. Einsteinian gravity thus emerges as a thermodynamic consequence of discrete informational quanta seeking equilibrium. This mathematical derivation culminates in the unified Einstein equation, or QIR. Central to this equation is the variable phi, an informational potential that structurally modulates the effective spacetime metric. The presence of phi carries an implication for relativistic kinematics. The local speed of light is no longer a global static constant. Light follows a kinematic identity formula, where its velocity is dictated strictly by the local informational potential. As the equation indicates, the speed of light is a function of the underlying potential at a specific coordinate. The universal speed limit is a structural boundary, programmed directly by the density of the underlying quantum substrate. The VSD framework addresses macroscopic astrophysical anomalies, like flat rotation curves in spiral galaxies. Here, outer stars orbit impossibly fast for their visible mass. While standard physics assumes a halo of undiscovered particles, the VSD model looks to many worlds multiplicity, specifically disconnected branches. Here, disconnected branches are classical geometries that have decohered, but still occupy the same 4D coordinate volume. These dissociated ghost worlds do not interact via electromagnetism, but they still contribute to the local slice density of the block. This additional bunching provides the informational energy momentum required to explain gravitational lensing and the rotation effects we attribute to dark matter. Dark energy arises from baseline branching pressure. The unitary evolution of the universal wave function requires a minimum rate of state-space splitting, which manifests as a force driving the expansion of spatial slices. The dark sector manifests as the macroscopic gravitational shadow of adjacent parallel quantum realities. The VSD paradigm unifies the timeless eternalist block universe with the uncollapsed unitary evolution of the quantum wave function. In this framework, the static geometry of configuration space replaces dynamic forces and messenger particles. Large-scale astrophysical anomalies are reframed as mapped structural features of the 4D manifold. Gravity, time, and cosmic expansion are the perceptions of an observer processing the dense branching geometry of a timeless quantum multiverse.